right, hello everybody and welcome. Today we are going to learn a little bit about polynomial graphs, specifically degree, end behavior, x-intercepts, roots, solutions, zeros, and multiplicity, and get an idea at sketching these graphs. So the first thing we're going to jump into is degree and lead coefficient. So degree is the polynomial of the highest degree of the exponent of the variable. That is when it's written in its expanded polynomial form that we're going to see in these first few examples. And the lead coefficient will lead us to the end behavior, but specifically it's what sign that term is, and it determines the direction that the graph points as x approaches infinity to the right. So here we have three functions, all in expanded form. So what we're going to look for is the highest exponent here on the variable. I see that being a 4. So this is a degree 4, and that lead coefficient is negative. So it's -7 there because the exponent 4 has a -7 in front of it. It's not based on what comes first, even though it's called lead coefficient in this case. Second one, again, we're going to look at the highest exponent, which is going to be 5 here. And notice that -3 is the coefficient on it. So degree 5, lead coefficient negative. Finally, highest exponent, 6. So that means a 6th degree polynomial with a lead coefficient that's positive. Now, we're oftentimes going to see it in a different form, which is like this, factored form. In this case, it's going to look a little bit different. What we're going to look at here is if we were to multiply these two binomials together, I have an x to the third and essentially an x to the first that I'm multiplying together. So you're going to add those values together to get a degree of 4. And the lead coefficient is negative. Here we are just looking at what's in front because it's all being multiplied together in factored form. Again, in this next one, look at all of those exponents. That's essentially an x squared. That's essentially an x to the first and another x squared. So that is a 2 times a 1 times a 2. But we're adding exponents when you multiply them together. So that is degree 5, and here the lead coefficient is positive, again, based on that 5 in front. Finally, you're probably getting the hang of this. This is to the second, this is to the first, so you might be thinking, oh, it's a 3rd degree. Nope, it is a 4th degree because that x in front is an additional x value to be multiplied in, and the lead coefficient, again, is positive because it's a positive in front. All right, we're going to build some skills together before we get to sketching, so let's continue by looking at a couple examples that we already know about. The first one is y equals x squared. Let's just think about what that graph is. That is a parabola. I know the vertex at the origin, over 1 up 1, over 2 up 4. A rough sketch of a parabola. That's pretty good. Next one is the cubic. Cubic has a point of inflection right here at the origin. It goes over 1 up 1, over 1 down 1, and then over 2 up 8. All the way up here. Oops. And over 2 down 8 as well. So this graph's not something like this. Flattens out at that point of inflection where it changes concavity actually there. And we want to think about what is happening. So here, the degree is even in the first case, and I could look at a bunch more examples, but I'll save you on that one. When the degree is even, we notice the ends of the graph both are going up. And even if we reflected it down, it's still both going down. So what I say is that the ends of the graph agree or point the same direction. And then on the other side, here we've got a cubic, an odd degree. Every odd degree, the ends of the graph, I say they disagree. So they point opposite ways. One goes up and one goes down, left and right. All right, so let's use that on some specific examples. Here we have a few random sketches of graphs. We want to determine the end behavior and what that degree is. So I know right away the degree on this is going to be an odd degree. Function because one's pointing up, one's pointing down. There's 2 ends to it. And I can keep going down the list here. Well, this one's going to be even because they're both pointing up. This one's going to be even because they're both pointing down. They disagree. Or sorry, they agree. They agree. And the last one, I got to have myself, the last one is an odd degree based on the fact that one to the left is pointing up, to the right is pointing down. Now the next is how we write the end behavior. And for the end behavior on each of these, it's kind of two parts because the graphs essentially have two ends we're looking at. What is the left and what is the right end behavior? So in this first graph, my left end behavior is where that graph is going to the left, and that's going to be down, but the way we're going to write that is, since it goes down forever, we'll call it negative infinity. To the right, that's going up, so I'm going to call that infinity. All right, let's continue. So again, to the left on this graph, I see it going up, so we call it to infinity. To the right, I see it also going up, so also infinity. Let's keep rolling. Left, negative infinity here. Right, also negative infinity. So notice on these two in the middle, they are even, and their end behaviors agree. That makes sense. That checks out. That's how it should be. And the last one on the left, we're going up, so positive infinity. Right is going to be down, negative infinity. So again, odd, they disagree. All right, let's keep our skills building here. Now we're looking at some equations, or we're combining a couple ideas. So the first part's saying a graph of degree n has at most blank zeros. So graph of degree n has at most n zeros. N being, I don't know, we're still going. Has at most n zeros. So a third degree polynomial has at most 3 zeros. A graph of n degree n has at most n minus 1 turning point. Think of a basic example, a parabola. That's an x and y axis. It has at most, so the degree is 2. It has 1, 2 zeros, and the turning point is just the vertex there, 1 turning point, or 1 local extremum. All right, let's go through this quick example together, then you'll have one to try yourself. The degree, I see it in factored form, so I'm just going to add those two together. Degree is 5. We'll say the maximum number of turning points is going to be 1 less than that, so 4. The zeros are the x values. Well, it's where the graph crosses the x-axis, but it's the x values that yield a 0 as a result of a function. So it's the x values that make either that or that equal to 0. So x equals 2 and negative 1. There are 2 places where that function is 0. And finally, the end behavior. Remember, we are doing left and right. So on the left and on the right. To know just from the equation without graphing it, I'm going to look at my lead coefficient. My lead coefficient will always, in this case it's negative 6, but negative's all I care about. Lead coefficient will determine your right end behavior. Since it's negative, to the right, it's negative infinity. Then how do you figure out the left, you might be thinking? Well, remember what we said. If the degree is odd, then the end behaviors disagree. So, left end behavior, positive infinity. Easy as that. All right, let's do it again with the second one. I see, well, I have an expanded polynomial form, so I do not have to add the exponents. The degree is 3. The number of turning points, I should say max number of turning points, is 2. Zeros is where I get stuck now. I get stuck because it's not in factored form. So this guy, I got to factor. So I'm going to sneak in here. It's going to be a little tight, but I'm going to factor this. The first thing I know I want to do is factor out an x, because I can factor out an x from all 3 terms. And then I see a little more factoring needs to be done. So again, I'm going to squeeze it in here. The x is going to stay in front. That is my factored form. Notice how the degree is still 3 because it's like an x to the first times x to the first times x to the first. And now I got my zeros. Be careful. A lot of people miss one of the zeros here. The first zero that a lot of people miss is 0, because that x in front, that gives you a 0 at 0. And then 5 and 6. You could have said 6 and 5. That's fine. And again, left end behavior, right end behavior. Every single time, the right end behavior is based on the lead coefficient. Lead coefficient here or here, wherever you want to look, is positive. So the right end behavior is positive infinity. Since the degree is odd, the left end behavior will disagree. It's going to be negative infinity. All right. I have a couple for you to try right now. So let's see. There you go. I do want you to take a moment and pause the video and try this out. If you do get stuck on the second one, I have a hint for you to factor this. This will be your first step. And then you can factor a little bit further. But go ahead, try out these two, fill them in on your sheet. And hopefully you've done so. So now these are your answers. Notice again, I've already drawn in there that lead coefficient gives you your right end behavior. Okay, time to add on one last piece and then we're ready to sketch. Multiplicity. Multiplicity is the number of times a polynomial has a 0 at a given point. This is an example of a multiplicity of 1. This equation would look like y equals x minus 1 to the first. So we say this just crosses through. Goes right through. Crosses or pierces, you might have heard, but it goes straight through the x-axis. When compared to this equation, which would look like this, squared, that's a multiplicity of 2, and this is one that I think is all familiar. That's when we say it bounces. It bounces off the x-axis and stays on the same side of the x-axis. This should be familiar as well. This is x minus 1 cubed, a multiplicity of 3, and we say that flattens and crosses through. It does go through the x-axis, but it does a pretty distinctive flatten first. And finally, this is a multiplicity of 4, so it would look like x minus 1 to the 4th. And what we see is, and we don't see this a ton, honestly, but it's a flatten, bounce. Kind of combines the second and third. But what's important is it bounces. It still stays on that side of the x-axis. All right, we're ready to put it all together to get some sketching. I will sketch a couple, then have you try a few out yourself. So I've got it kind of scaffolded out here so we can list everything we need before we start to sketch, but eventually I think you'll be able to just go for it. First thing is degree. I'm going to add up 2 plus 1 plus 1 to get 4, even degree. Interesting. Lead coefficient is positive. Okay, this is going to help me with my end behavior now, these two things. So I need a left and a right end behavior. The positive lead coefficient tells me right away the end behavior on the right is positive infinity. On the left, I have to go back to my degree. The degree is even. So my end behaviors will agree, also positive infinity. And finally, zeros. Zeros are what x values make the function 0. So I see -6. I see 1. I see 3. But what it also says is with multiplicity, because that's going to help me graph. Multiplicity on the 6, the root of 6 is a 1. On the 1 is a 1. On the 3, it's a multiplicity of 2, which means I'm going to put a little note on that. I got to bounce there. I got everything I need. I'm going to go for the graph. There's a bunch of ways you could go about this, but the way I prefer is definitely plot your zeros first. So -6 is going to hit the x-axis. 1, it's going to hit the x-axis. 3, it's going to hit the x-axis. Beautiful. Now, beyond that, I want to look at the end behaviors. To the left and to the right, it's positive infinity. And what that helps me do is it says, all right, to the right of my rightmost 0, my graph's going up. So I'm going to put an arrow up there just to say, all right, that's where my graph should end over there. And same thing over there. They're both going to end up, so I put my end results there. And then I have to weave through these zeros based on their multiplicity. I see a multiplicity at -6, it's 1, which means just cross it right through. So I'm going to start my graph. And people often get here and they're like, well, how do I know how low I go or how shallow I go or where do I go in here? It really doesn't matter. This is a sketch. We're getting a rough idea of it. But I know I'm going to be below the x-axis. I'm going to come up and be crossing back through, because again, a multiplicity of 1. And then at 3, when I approach it, I'm like, I'm just going to do a little loop there. You can go higher if you want. You don't have to. I see I'm going to bounce. So there's my final graph. It made sense with where my end behaviors were and the bouncing and the multiplicities. Cool. First graph down. Let's do one more, and then you will practice. So let's do the same thing. Degree of this guy. Let's see. I see it to the first, to the first, to the third. I'm going to add those together to get a degree of 5. And the lead coefficient, that -3, is just going to be negative. That's all I care about. The left and right end behavior. Okay. Remember, the lead coefficient is negative. That means when it goes away to the right, it's going to be negative. So to the right, negative infinity. To the left, since the degree is odd, it's going to disagree. So infinity. And the zeros. Don't miss that guy in the front. You're going to throw your graph off. It's not going to really make sense. The first degree in the front, is just x by itself. It's 0. -5. 7. And the multiplicities below them. Multiplicity of 1, 1, and 3. And I'm going to note, I want to flatten. But it still crosses. All right. Graphing time. 0. -5. 7. Those are the 3 places my graph will touch the x-axis. And end behavior to the left. So to the left of the leftmost 0, it's positive infinity. So it's going to go up there. To the right of the rightmost 0, negative infinity. So I'm going to sneak it in down here. Because it's got to be to the right of that last 0. Now you can choose which way you go. I typically go left to right just because that's how you typically read a function, but it really doesn't matter in this case. Oh boy. It's kind of hard here. Let's try it one more time. We're going to cross at -5. We're going to cross at 0. When I come to this last 0 over here, 7, I know I need to flatten. So to flatten, best way to do it is just come down like about a unit early and just flatten on the x-axis for a block or so. And then you can come down. Notice my arrow I didn't quite hit, but that's fine. I got the idea of it. That graph looks gorgeous. All right. One more time. I'm going to give you 3 to practice. So please pause the video. Try these out for yourself. I will reveal the results in a minute. By a minute, I mean right now. There you go. So you might not need all of the scaffolding to list everything. If it helps, do it. But eventually you'll get to a point that you may not. All right, one last topic we're going to do here. You guys are doing great through this. The final thing is determining an exact equation of a graph. We're going to do 2 quick examples. So we always go like, hey, given an equation, graph it. Now here's your graph. Tell me the equation. I see a 0 and another 0. So my equation I know is going to look something like x plus 4 and x minus 1. Great, but I'm definitely missing pieces. The first thing is the fact that it is bouncing. It bounces there, which means I need to put a squared on that binomial. That represents the bounce. Second thing I'm missing is the fact that I don't know, like the vertical stretch or compression going on here. It looks like a pretty tall graph, but I don't really know. So what that is the same thing it was for all of our parent functions. It's an a value. So you just have to solve for an a value. And how do you do that? Well, you're given an x, y coordinate point. So plug in 0 for x, 32 for y, and solve it out. Plugged in my zeros for x, 32 for y. Now it's just some algebra. 0 plus 4 is 4 squared to get 16. Excuse me. So 32 equals negative 16a. Divide by negative 16. A is negative 2. That's tremendous, but don't forget, you got to put it into a final equation, which is going to look like this. I did all that good work to get the a value. Don't forget something silly like leaving off that multiplicity 2 or forgetting to write the actual equation. That's our whole goal, right? So make sure you do that entire thing. All right, one last one. Why don't you, if you're feeling confident with it, you can go ahead and pause me and do it yourself. I'll go through it pretty quickly here now, though, as well, in case you want to do that. So I see some zeros. Negative 3 and 4. So x plus 3, x minus 4. But I see this is definitely flattening out here, which means that's going to be a third multiplicity, multiplicity 3. And don't forget a value. To find that a value, I'm going to use this coordinate point 2, negative 10 that was given to me. So negative 10 is my y I'm plugging in. And what is it? 2 is my x. And algebra skills. Do what's in parentheses first. That's going to be a 5. 2 minus 4 is going to be negative 2. Cubed is going to get me negative 8. Keeping that negative 10 on the other side, it's going to be negative 40a. Be careful with your last step. Don't you tell me that's a 4. It's 1/4. So, final answer, 1/4. X plus 3, x minus 4 cubed. It's always good to double check yourself. Yeah, that is a positive lead coefficient graph because the right end behavior is up. And fourth degree makes sense because the ends agree. Wonderful job on this today, guys. You got your practice homework to work on, but you don't have to worry about that. Good job.